This is Biweekly Contest 123 Answers Discussion. Welcome to Alex Does LeetCode. Please like and subscribe if you enjoy my content. We're going to start with question number 1. This question says, you're given an integer array of size 3 which can form sides of a triangle. Triangle is equilateral if it's all the same sides, isosceles if exactly 2 are equal, and scalene otherwise. Now, there's one other type of answer, which is if they can't form a triangle, then you return none. Alright, this question is not very difficult, so I'm going to go through it very quickly. Basically, what you do is you want to start by checking if this is a valid triangle at all. And to do that, what I did is I just sort them, smallest to largest, and I want to check if these 3 numbers from smallest to largest form a triangle. It will fail to form it will only form triangle if the first 2 numbers, the 2 smaller numbers, is smaller or large added together is larger than the third number. So a number like this, let's say 1, 2, and 10 will not form triangle because the first 2 numbers added up are too small to complete the third side. Or the other case where it doesn't form a triangle is all 3 numbers are 0. So if nums2 is 0, or this thing doesn't happen, then return none. Otherwise, you do the check. All 3 are equal, equilateral. If any 2 of them equal, isosceles. Otherwise, return scalene. This should be a pretty straightforward problem, and I will not spend too much time on it. Question 2. Number of ways to place people. Okay, so we've talked about this. Okay, let's go through a question for those of you who are on the board. So this is a very long question description, but basically what it says is that you're given a bunch of points. You're given a bunch of points on a 2D plane. Alright, you get to put Chisato at one of them and Takina at another one. Alright, so you have to put, given a list of points, you have to choose 2 points. One will be Chisato, the other one will be Takina. Alright? And then the way it works is, there are 2 rules. 1, Chisato must be left and above Takina. So for instance, in this case, neither of these can be Chisato because Chisato need to be left off. So this guy is not left off. And this guy is left off, but it's not above. So Chisato needs to be left off and above Takina. Right? So for instance, this case, same thing. You cannot have, there's no Chisato, right? Chisato, no point is left off and above another point. So you can't have Chisato and Takina here. So right here in this example, you can put Chisato here. You can put Takina here. That will be legal, okay? So 2 conditions. First one, Chisato must be left and above Takina. 2 is nobody else must be in the rectangle between them. So in this case, this works because there's a rectangle between them, square in this case. There's no other points in it. There's no other points in it. So this is correct. This one also correct. Okay? But this one is actually not correct because let's say let's say Chisato is here. Oh. Let's say why is it like this? Let's say you have Chisato here and Takina here. Alright? Chisato is left and above Takina, yes, but there's somebody in there. So this is not valid. So the answer here is 2. 1, 2. Okay. So now that and this one, Chisato and Takina, they don't have to actually form rectangle. This is a line, but line is also a very skinny rectangle. You can think of it that way. Now that you know the problem, let's try to take a stab at a solution. So how do you do it? So the way I did it is the first thing I want to do is to sort all the points left to right. I sort all the points left to right. Because I know Chisato is always to the left of Takina, right? So I sort all the points to left to right. I'm doing one other thing here that's kind of tricky. I'm not just sorting points left to right. I'm also saying if the points are on the same line, the points whose y is larger is first. Yeah. So I'm basically saying I take all these points, I sort them first by their x-axis, by x value. But if two points have the same x, then look at the y. The one with the bigger y goes first. So smaller x goes first, but if x are equal, then bigger y goes first. And the way to do this in Python is actually very convenient. I can just have a lambda function that says I want to sort x first, and then I want, well, this is point, right? First sort by their x coordinate, and then I sort by the negative of their y coordinate, and this will allow me to sort the points by their x coordinate first, and if their x are tied, the one with the higher point y wins. And so what this does is it basically guarantees that everybody who is on the left, who is on a smaller index, is a valid Chisato for the Takina on the right. Right? So I've sorted all the points. Any point that is smaller in my list is a valid Chisato. So after that, I do a nested loop. Chisato and Takina. Takina will start from C plus 1 because you have to be the right of the guy. And then now, the other thing I know is that the people who could possibly between them are everybody between C and T. So C is on the left, T is on the right. I have another for loop here. So here is a check. This is another for loop. Check equals true. And then I have J that goes from C plus 1 to T, between them. And check. Now that I know that their x-axis are between them, all I have to do is to check the y-axis. So I check the y-axis. If the y-axis is between Chisato and Takina, then I know this breaks the invariant, and check is false. If check is true, then count equals count plus 1. And this runs well. And this actually also works for question 4. Alright? So that's question 2. Now I'm going to go on to question 4. I'm going to jump ahead here, because question 4 should be the same as question 3. Actually, question 2. So I used the exact same answer from question 2 to question 4, and it worked. Okay? So the only difference between question 2 and question 4 is that the size is much larger. It says the n is much larger. That's all. Question 2 is 100, question 4 is 1000. But the thing about the thing that the thing is, if you use this sorting technique, you should be able to still get it, right? This one did not time out for me. It took a while, but it didn't time out. So if I run it, and I don't know why it timed out for some people. My guess is maybe you didn't sort this correctly, which caused you to have to examine more points than necessary. Yeah. If you didn't sort this correctly, then maybe that might have led to some issue. Question 3. Let's start by reading question. You are given an array nums of length n and a positive integer k. A subarray of nums is called good if the absolute difference between the first and last element is exactly k. In other words, ij is good if nums I minus ums j absolute value is k. Okay, let's take a look at some examples. Here, 1 and 2, k is 1. So 1 and 2 will be an example of a good subarray because 2 minus 1 is 1. Same thing, 4 and 5. 5 minus 4 is 1. So 5 and 4 is also a good subarray. In fact, all adjacent pairs are good at subarray in this example. So all adjacent pairs, 1, 2, 2, 3, 3, 4, 4, 5, and 5, 6. So what we then do is we find the maximum of these guys. We add them up. The sum of this guy is 3, this is 5, this is 7, this is 9, and finally this is 11. So the maximum subarray sum for good at subarrays is going to be 5, 6, which is 11. So in this example, we actually have two good subarrays. K is 3, so minus 1 to 2. This is a good subarray because the difference between minus 1 and 2 is 3. And likewise, 2, 4, 5 is also good because the difference between 2 and 5 is also 3. Now note that there are numbers inside them. Note that these numbers are not always in order. There's like 3 before minus 1, and some of them can be negative, which could be a bit of a pain. Now, given all the two good subarrays, we find the one with the biggest sum, which again, 2, 4, 5. So again, the answer is going to be 11. And finally, for here, we have two good subarrays, minus 1, minus 2, minus 3. Because the difference between minus 1 and minus 3, let me see. So yeah, the difference between minus 1 and minus 3 is going to be 2. And the difference between minus 2 and minus 4 is going to be 2. Notice in this case, the guy on the right can be smaller than the guy on the left. Right? So we're taking the absolute value. It doesn't matter which one is which. In this case, minus 2, 3, minus 2, minus 3, sum is minus 6, is a larger one. Which is kind of weird because now the larger number is actually the largest good subarray sum is actually a negative number. So, well, let's start with how we're going to do this, right? So the most straightforward way, and the way that I think a lot of people started with, including myself, is to think of this as a brute force. Well, we want to find all subarrays. Well, that's not too hard. We have some kind of nested loop. We have like a nested loop that says, I in 0 n for j in I plus 1 n, and then we have subarray equals to I j, right? And then you do the check num I minus nums j equals k, blah 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 blah. And so you can do this. This actually works. You give the right answer. But the problem is this is O(n) squared. Because there's two nested loops. So the complexity is O(n) squared. And O(n) squared is not going to work when n is 10 to the power 5. Not in LeetCode anyway. So we have to somehow modify this and make this a little bit faster. Now the other thing, when I came to this problem, the first thing I noticed is that you don't actually, right? You don't need to go through the whole list to find out what j is. You don't need to go through the whole list to find out what j is, because based on what I is, you can calculate what value you need for j. Take for instance this guy. If my I is 2 and nums I is 2, then I know nums j. If nums I equals 2, then nums j must be equals to 2 plus k or 2 minus k. Because we want the difference between the two of them to be k. So nums j is equals to 2 plus k or 2 minus k. So we can straight away jump to 2 plus k, which is this 5 over here. Or we can do 2 minus k, which is this negative 1 over here. So we know the numbers, we know nums I, we know nums j. How to get j? Well, we can do that by maintaining some kind of lookup. We maintain some kind of lookup. The lookup basically says, well, it's basically a dictionary of some kind. So the lookup says that the key will be the value, right? And the value of the dictionary would be its index. So this is one solution. So with this, you can actually make our solution a little bit better. We can upgrade our solution. Instead of this nested loop here, we find out nums target j equals to nums I plus k. Let's do nums I plus k first. And then we have some kind of lookup to get j. And this should be O(n) time. And then what we do is we sum from nums I to j plus 1. Yep. So this works. But there's a catch. This is actually still too slow. Because when you do the lookup here, this thing will not return just one number. Right here, there's only one. There's only a 5 here. But imagine, okay. Imagine a test case. Let's see if I have test case. Yeah. Imagine this test case over here. This test case over here. Let's say I is 5. And then I think, yeah, I is 5, K is 8. So I'm looking for 13s. So 13s, where are the 13s? I have to look for 13s. There's a whole bunch of 13s. Well, maybe there's not a whole bunch of 13s. But yeah, there should be a 13 somewhere here. There's a whole bunch of 13s, right? So when I actually ran this array is of size like 100,000. When I ran this, there was something like 5,000 13s. So this is fast. This technique that we use is fast, but this sum still takes a long time because there are many, many j's. So for j in j's, you have to do this, right? So this is still very slow because j's can be, it won't be the size of n, but it's going to be sort of kind of large. And then when you have sums, unfortunately, it's going to be linear time. So that makes it kind of suck. So that's the problem that we have. So I'm going to talk about our third solution, which actually does work. And the idea here is instead of storing a lookup, this j's will look up, we're going to do a few things. One, actually, let's have an intermediate solution. So the first thing we want to tackle, this solution sort of works, right? But this sums, we've established that sums is slow. Sums is so slow because sums is linear time operation, and we're going to, because it's inside this, two nested loops, this linear time operation is going to kill us. So instead, what we want to do is to have this idea of a prefix sum. And the way the prefix sum works, it basically stores the sum of all numbers, excluding the current number. So the prefix sum, so instead of doing sums, I to j, I can just take the prefix sum of j minus the prefix sum of I. Yep. So prefix sum, for instance, let me be very concrete here. So prefix sum, for instance, if I have minus 1, 3, 2, 4, 5, a prefix sum will be the sum of all numbers before it. So minus 1 prefix sum will be 0, 3 will be minus 1, 2 will be minus 1 plus 3, which is 2, 4 will be the sum of this, and this, which will give me 2, I guess ironically it will be 4. And then this will be a prefix sum of everything before, which is 8. So prefix sum is easy to calculate, just add the nums n each time. So what we want to do is we want to find the difference between, if we want to find the sum of this and this, we simply take the prefix sum here, 8 minus 2. Oh, this is not actually correct. Let's backtrack a little. Let me see if what I go wrong here. Oh, sorry. I need to add. I need to add itself. So 8 minus 2 plus 5, right? You get it. Basically take, the sum 8 is the sum up to 4, the first 4 elements, minus the sum here, and then you add yourself. So 8 minus 2 plus 5. So this makes calculating the prefix sum really easy. This makes calculating the sum of the range really easy. So it's no longer linear time. It's like basically one time. So this is fine. This is fine. I actually tried this, and then I ran into another problem, which is now j. There's a lot of j's. Yeah. So we just saw, right, there can be a lot of j's. So this prefix sum, even though it's on, has repeated many times. So instead, we have a fourth iteration, which is instead of storing a whole bunch of lookups, I'm going to store only the prefix sums. And not only that, I'm going to store the smallest prefix sum, because I'm going to do I minus j anyway. If I'm going to do I minus j, prefix I minus prefix j, well, I want to find all the different j's, and I'm going to find the largest one. Well, the answer is the guy with the smallest prefix. Yep, that will give me the largest answer. So this is how we came to our final solution. It looks something like this. You see, best equals minus infinity sums. This is our prefix sum. Current equals 0. So we keep like a running total, right? We keep like a running total. So for nums equals nums, and this might be easier to illustrate, minus 2, minus 3. Okay, this might be easier to illustrate when we actually have numbers. So for right now, nums equals minus 1. Right, current equals to 0. Okay, and then the prefix sum for this guy is so far is 0, because it's just starting out. So for nums equals pair 1, where that is so num equals to minus 1, num plus k is 3. So k pair 1 will be 2. Right? And so pair 1 we have not seen before. So we're going to ignore it. So pair 2 we've also not, pair 2 is minus 3, we've also not seen anything before, and then we're going to ignore it. Okay, where it gets interesting, let me just fast forward a little bit. You know, the prefix sum of minus 1 will be 0. The prefix sum of 3 will be minus 1. So it's the sum of everything before it. The prefix sum of 2 will be 3 plus 1, which is 2. Okay? So now we get to 2. Now it gets to interesting. So what we want to do now is we want to say, hey, we want to look for pair 1 in sums. So pair 1 is minus 1. And so far, our prefix sum, let's see, how best to express this. Our sums for minus 1, the best we've seen so far is 0. Okay, the best we've seen for 3 is minus 1. The best we've seen for 2 is 2. So we're up to here, right? We're up to this line of code. We say 2, our nums is 2. So nums plus k is going to be 5. We actually haven't seen this yet. So we are here. Nums minus k is going to be minus 1. And we're going to see what's the best sum we've seen. Well, the best sum we've seen is actually 0. Right? It's actually 0. So we're going to take that one. Now, what happens when there are multiple versions of the same thing? So when we get to here, we have actually 2 minus 1s. This guy's prefix sum is 0. This guy's prefix sum is actually minus 9. is actually 9. So which one do we store? We actually store just the 0. We don't have to store the minus 9. Right? That's what this line of code is doing over here. If current is smaller than some sums, this is updating a prefix sum, but it only update if the new prefix sum is smaller than existing one. Why? Because we're always subtracting the prefix sums. We're always subtracting prefix sums. And if the prefix sum is going to be higher, then we know that we're not going to get a better result. So we're keeping the prefix sum is basically the smallest prefix sum we're seeing for this particular number. So for -1, the two prefix sums that we've seen are 0 when it's at the beginning, and 9 when you have -1 plus 10. Where you have -1 plus 10 for this guy over here. So we always keep the smallest prefix sum we see. So in another example, let's say instead this was -1 and then 10 and then -1 again and then -100 -1 and then 2. Okay, well, what's the best prefix sum we're seeing so far? For here, we see this will have prefix sum of 0. This will have prefix sum of 9, 10 minus 1. This will have prefix sum of 9 minus 1 is 8. And then so this is minus 92. Okay, so this one is actually the one we keep. So this will be minus 92. And when we find a match, when we find a pair for 2, we want to choose the guy with the lowest prefix sum we've seen so far, which will be this 92. We don't need this, and we don't need this, because this minus 92 will give us a better result for when paired with 2. I hope that was helpful. This is actually not that easy to grok, even though it's only a few lines of code. So I do this for pair 1. Pair 1 is basically num plus k. So for the example above, for this example, let's say nums is 2, then pair 2 will be nums minus k. 2 minus 3 is minus 1. So this is the part we're at. We'll find the one with the best. We find the current sum is, we find the one with the best prefix sum. With the smallest prefix sum, we update our best if necessary. And then we update our current. So this current is running total. So that's how we quickly determine what is the sum of all the numbers that come before us using current. And finally return best. And if you run this, this is accepted. This will work. Okay, I hope that was helpful. Generally for contest discussions, I don't spend a lot of time after the contest to do a discussion. And this means that sometimes for the complex questions like question 4 and this question 3, which is really complex, I don't always spend enough time. I'm not always able to explain it with the full detail that somebody will require if they are coming to this contest code. So let me know in the chat or in the comments if this is actually helpful to you, or if you prefer that I spend more time explaining, because I'm happy to do that too. If you want to spend more time explaining, or you want a separate video on all these hard question 3, question 4s, then let me know. Meanwhile, as usual, if you enjoy my content, please remember like and subscribe. It helps us out a lot, and it also notifies you when I post a new video. That's it for today. Thank you very much for joining the stream.